So this the same set, the same form here, but instead of operating on the value, so just x equal to this guy is a particular value, right? This is our vector. We're gonna use the polynomials. So, and that transformation is it's quite not quite common, but it has I've seen it before, because the idea is that if you have a function, right? You have a function, and you wanna, especially with polynomials, because polynomials have is a linear combination of some base vectors. You, instead of having relationships hold true, so you want to test with that this guy is equal some other guy, right? Yeah, you are saying you're going to build a polynomial so that at given axis value, so this is x, right? This x, if you evaluate the polynomial is something that is of the form a plus bx plus cx2 plus dx cubed and so on and so forth, right? So you can evaluate this guy at x equals 0, that gives you a. If you evaluate x equal 1, that gives you a plus b plus c plus d. If you evaluate x equal 2, you're gonna have a plus 2b plus 4c and so on and so forth, right? So if you make this polynomial with a certain form that we're going to do now, we can transform a set of equations that have to be true at 4 sets, right, into one polynomial equality, such that if you evaluate at the polynomial at 4 different points, you're going to recognize the 4 or original set of equations. So the trick here is that we are saying, we're going to say that if we do x equal 1, we're going to match this polynomial with the first equation, with the first set of equation. If we do x equal 2, it's going to match the second set. You do x equal 3, it's going to match the third set, and if x equal 4, it's going to match the fourth set, right? So that's the idea behind it. So how do we do this? So first of all, we need to determine the degree of this polynomial. Right. So this polynomial here is degree 3, because the highest exponent is 3. And there's a nice property that if you have a polynomial of degree n, so if this last value here is n, then there's only one polynomial of that would go through n plus 1 points that are given. So for example, that what it means is that if you have n equals 0, so that in that case your polynomial is just a constant because nothing else, then there's only one polynomial of degree 0 that passes through 1 point, right? So that's pretty obvious. If you put 1 point out there, then the polynomial of degree 0 constant that goes through that point is that line here, right? X equal y equal that particular value a. If now you're saying that you have 2 points, so no, the line doesn't work anymore. You need more degrees of freedom, because the polynomial of degree 0 is very constrained. You only have one parameter, so it's only this particular shape. But if you want to have more degrees of freedom, you have more variation basically possible, then you have to add more degrees. And if you have 2 points, then you just need to add one more degree. So you have to have a polynomial of degree 1, because only one, x power 1 basically here, and it has 2 parameters. So that goes through 2 points. So that's this guy is a line, so it goes a line like this. And then if you have 3 points, so now if you have 3 points like that, so you need 3 points, then the line is not good enough, right? Because that point may not be on that line, and then you need to add one more degree. So you go to x cube, so ABC now, because you have x cube, and you have a parabolic, and that should be something like, kind of looks like this, right? And again, if you have 4 points, then this guy could be here, and that the parabolic would not be enough, and you need a cubic. So something like, I don't know, so maybe something like that, and then it curves back, right? And so on and so forth. So if you have n points, you need n minus 1 degree, because n minus 1 means n minus 1 degree, n minus 1 degree, because then that gives you n parameters, because the first parameter is degree 0, right? Okay, so that being said, since we have 4 equations, right, we have 4 equations here, yeah, four gates, 4 sets, 4 equations, we're going to need a polynomial of degree 3. So we're going to be it's going to be something of the form a plus bx plus x2 plus dx3, right? So it's going to be a cubic, right? And what we can choose arbitrary point, right? So we choose, for example, x equal 1, 2, 3, 4. We have four points, 4 values of x, and then we want to make we want to make this polynomial match this constraints. A constraint. Where's the first constraint? Yeah, this first constraint. When x equal 1, right? So now here we have a, which is just the values here. Now a is going to be a polynomial. Right. What we want is that, so we're going to have 6 polynomials, right? It's against the 6 variables, right? So we're going to have 6 polynomials. So we have 6 polynomials, and a, b, c are going to be these polynomials. So you're going to have polynomial a1 to a6, and b1 to b6, and c1 to c6, each of them being of degree 3, right? Such as if you do a1 evaluated at 1, and then you use a1 evaluated at 1, and then b1 evaluated at 1, and a6 here, right? b6 evaluated at 1, and c1 evaluated at 1, and then c6 evaluated at 1. You're gonna have the first this guy here. This guy should be matched this guy, right? So what we do? We recognize that this means that a1 of 1 equals 0, because this term here has to match this term here, right? And then we have a2, right? a2 of 1 has to match this term here, so it must be equal to 1, right? And then a3 of 1 is equal to 0, a4, a5, 6, so 1, 1, 1, and it's going to be 0, 0, 0, right? So that it matches this guy. And then same for b, you have b1 of 1, it should be 0, and then b2, b3, b4, b5, b6, all of them evaluated at 1, coordinate 1, and that should give you 0, 1, 0, 0, 0, 0, right? So you have this one. Okay, you can do C as well, right? C, C1, C2, C3, C4, C5, C6. Give that 1. Evaluate that 1. And that should give you this one. So 0, 0, 1, 0, 0, 0. Right. And then that is for the first set. Then you do the same thing with 2 here. Instead of evaluate at 1, you evaluate at 2, and you use the coefficients that you have here. So at 2 is going to be 0, 0, 0, 0, 1, 0, 0, 0, and then 0, 1, 0, 0, 0, and then 0, 0, 0, 1, 0, 0, 0. Right. So I'm not going to write the other ones, but this first guy is going to be equation 1, and then you have equation 2, 3, and 4. Right. And by having, at the end, you're going to have, like, you know that A1 at 1 is equal to 0, at 2 okay, at 1 is 0, at 2 it's 0 as well, at 3 where's 3? At 3 is 0, and at 4 I guess it's 5, right? So A1 is like that, right? Because we are looking at this term here, this term here, then this term here, so this term here, this is the term of the second equation, and then this term here, the third equation, and then this term here, the fifth equation, right? So this is why we come up with this. And then you're gonna have the same with B1. Okay, actually you're gonna have the same with the similar thing with the A2, A3, A4, and A5 and A6, and same for B and same for C. Right? So this guy here, if you have a polynomial of degree 3, and you know the value at these 4 points. So this determines a cubic. There's only one polynomial of degree 3 that goes exactly through these points. Right? So if we're looking at the guy here, we have 1, 2, 3, 4, and it has to be 0, 0, 0, and then 5. Right? Sorry, it's 5 here. Right? So we want a cubic that goes like this, and I imagine that guy should be something like this, something like that. That'd be 0, 0, 0. So you can see the thing is that it's not going to be 0 everywhere. Right? It's just going to happen to pass through 0 for the values that you want, 0, 0, 0, and 5. But just because it has 3 zeros here doesn't mean that it's 0 everywhere, obviously, because you need 5 here. And it's gonna get like a zig and zag between the stuff, like oscillate quite a lot in order to pass through these target points. Right. So we at the end you're gonna have 6 polynomials of degree 3 for A, for B, and for C. Right. Right. And then these polynomials, they have also the same. They're also such that if you have the solution, your solution S, right, which we remember is X1, A, B, C, D. So this assignment of these wires, right? We still have AS times bs equal cs. So this holds true, except that here a would be basically a1, a2, a3, a4, a5, a6, that you do the scalar product with this guy, so times 1 x a b c d, right? You multiply by this, then the result is you sum the result, so you sum this because it's a scalar product, and the result of this is I multiply by the same thing with b, so b1, b2, b3, b4, b5, b6 with 1 x a b c d, right? Same stuff here with a big plus here, and then the same with c, right? But now these guys are actually polynomials, right? And you know that you have equality between this stuff, but not everywhere. Only at the point where x equal 1, 2, 3, or 4, right? So you know that these polynomials are equal at these points, not everywhere, just at these points, right? So this, you're gonna say like, what the heck do I do? Why do I go through all this thing here? It's because now we have turned the four sets of constraints into one constraint. Well, granted, it's a constraint on the polynomial, so it's kind of a bit like cheating, but it's still a good result, because now if you look at what we are doing here, this, right, is also a polynomial, right? We have a polynomial here, and we multiply by a scalar. So this is you just scale up this polynomial, and then you add another polynomial of the same degree, and then you add it, and so on and so forth, right? So this result here, you never increase the shape of the polynomial, because if you have something of the form, it's a polynomial, so it's where did I write it? It's something like this, right? And you multiply by a value. This just going to multiply every coefficient, so it remains a polynomial of the same degree, right? And then if you start adding polynomial of the same degree together, you're not going to increase the degree. You may decrease the degree, because if you happen to cancel the term, it would lower, but it's still a polynomial of maximum that degree. So here what you have is that your solution, your S, is a linear combination of these polynomials. What? Why so dark today? Okay, sorry. This is a linear combination, because these are weights basically assigned to these polynomials. So this is a linear combination of a1, a2, a3, a4, a5, and a6. And this is another combination of b1, b2, b4 with the same coefficient. This is very important that we have the same coefficient here, and also the same coefficient here. So you have three linear combinations of A's, B's, and C's with the same coefficient, such as that guy, which is now going to we call it really big A. So AS is a linear combination of well, I don't know how to call this guy. Okay, just call it A with a big A like that, let's say, times B equals C. Right. And again, these are all polynomials. So this polynomial degree 3, this polynomial degree 3, multiply this polynomial degree 6, this degree polynomial 3. They are not equal. They are just equal at these points. All right, it's equal at these points. All right. Okay, so another way to say this guy, right, is to say that A times B minus C equals 0. Right? Again, is 0 at these points. So there's a result that says that if you are 0, if you are a polynomial, right, and which happens to be 0 at these points, you must be a multiple of the polynomial that is 0 at this point. So there's the obvious polynomial that is 0 at this point is the one that is written as x minus 1 times x minus 2 times x minus 3 times x minus 4, right? So this guy, if you evaluate at 1, this term becomes 0, and then it's going to multiply with something. So 0 multiplied by whatever is going to be 0. So it's going to be 0 at 1, 2, 3, and 4. So this particular polynomial, right, is going to be divisible. So this guy will divide z. Or in another way, you're going to say that there's another polynomial h that multiplies z. Right, so z, if z is this dude, then a times b, so again the polynomials minus c, is equal h times z. Right, so this is the relation that we are looking for, and these guys here, this a must be a linear combination of this vector. B must be a linear combination of this vector and c as well, and a1 and a6 are only dependent on the problem that you are trying to solve, which is in this case this guy, right? We never used the actual solution in the calculation of this vector. So you can pre-compute, right? So for a given problem statement, you're gonna have you're gonna compute all this stuff and then come back with this particular polynomial here, this particular b and this particular c. So a, b, and a1, a6, we should say b1, b6, and c1, c6 are only dependent on the problem that you want to show the proof for, and z also, because z is actually has degree 4, so we need to know the degree, and this 4 is because you have 4 gates, right? We have 6 variables and 4 gates. So also z depends on the problem, and in practice, well, in more realistic cases, this is going to be way higher than 4 and 6, obviously, right? It's going to be like 1,000 of variables and thousands of gates, right? So this is really going to be very large, and it's not the polynomial that you can just figure it out without actually going through the calculation, right? Okay, so this is where we stop for this part, right? This part stops here, and had nothing to do with crypto. It's just like turning the original problem, which was this guy, right? We turn this original problem here into this problem here, right? And this conversion was like very systematic. We have derived a particular vector a of a vector of b, and a vector of c. They are all very specific to this particular problem, right? And we know that if you have a solution, you're gonna have a proper assignment for s, and then your assignment for s will be in such a way that this relation is true. And if you have a wrong assignment, if you miscalculated a, b, c, this stuff, if you have one of these guys wrong, then if I calculate that guy, this would not hold true. If I calculate this guy, this will no longer divide this stuff, right? So that's really the first step of the algorithm, this conversion, right? So now the second step is more like a practical thing. It's about how you show that you have actually done because as a prover, you're going to give you a, b, and c, and then h, right? And you have to do two things. You have to give a, b, c, h in a way that you don't give millions of kilobytes of data for this, because these are really, really large polynomials. They have thousands of degrees, so it's a lot of parameters, thousands of parameters. So you don't want to give so much, so that will no longer be succinct. So that's one problem. Second problem is you actually don't want to give A, B, C, because if you give A, B, C, this will help the guy who receives these values to have some clue about what linear combination he have used, right? So because A is a linear combination of this polynomial that we know about. Right? This polynomial is the problem statement, so everybody knows which polynomials they are. So if you give a linear combination, it could be a case there where this happens to give an idea of these parameters here, these values here, and then you seek that X, your secret, is one of the coordinates. So that's a second problem. So you don't want to you want to hide, so you want to be succinct. You want to also to be zero knowledge, so you want to hide the knowledge of, you want to hide S, and you want to be verifiable. So you also want to be sure that the guy who receives this stuff, even though you're gonna hide S, you have calculated these A, B, C, H properly. You're not making it up, and they are actually going through this particular. These are really combinations of A1, B1, A1, A6, B1, B6, and C1, C6. So that's the second part of the problem. Give something that is succinct, give something that is zero knowledge, and give something that is verifiable. And this is when we need to use elliptical curve cryptography. And so far, I think it was tedious, but obviously it's done by a machine, so you never have to do it manually. But it was not too strange, right? No, not too difficult. Right. So the next part now. So really, like, we stop here for, there's like two bridges coming to each other. We have one problem, which was converting this problem statement to this, and the second problem is how to actually prove that you have this, but without with fulfilling these conditions. And for this, we need elliptical curve cryptography. Right. So for the moment, we forget about this, and we go to the other stuff. Right. So if you talk about where we are in this, we are talking about we did this one, right? We did arithmetic circuits, we did the constraint systems, so we're actually doing this. And there's one thing in between I forgot about. It was a quadratic program, something, QAP. So QAP is when we turn that into a polynomial. So now we have we're going to talk about how to do this blind thingy, like blind polynomial evaluation and verification.